Okay, we're going to talk about the extrema of a function today. And extrema are the extreme values. So the minimum and maximum of a function on an interval are called the extreme values or the extrema of the function on the interval. They're also called, did somebody just take my picture or someone's picture? They're also called the absolute minimum or absolute maximum on the interval, respectively. Okay, when we talk about this, we're talking about the y value of the minimum or the maximum. So the highest y value or the lowest y value. So find the absolute extrema of each function on the given interval. Or we're talking about like a point. So you can either name the point or you can name the y value. So for the absolute minimum on A, what point is the absolute minimum? 0, 1. And what is the absolute maximum? 2, 5, yeah. Let's name it as a point. Okay, on B, how about the absolute minimum?
0, 1.
Okay, still 0, 1. How about the absolute max? Okay, right before 2, 5. Is there a specific point that's right before 2, 5? No. Okay, we can kind of think about it as kind of a limit, but there is no absolute maximum. There's not one specific value that is the highest point on that graph. All right, C, how about the absolute minimum? Yeah. On C, there is no absolute minimum because that y value, there's a hole at that point right there. So we're getting closer and closer and closer to y equals 1, but never actually touching y equals 1. All right, is there a maximum? Yes. And it's at 2, 5. All right, so the rule of thumb here is that a function doesn't necessarily have to have an absolute min and or an absolute max, and continuity can definitely affect the existence of extremum on the interval. So if your function's not continuous, it's going to affect whether or not you have a minimum or a maximum. All right, and that brings up the extreme value theorem. The extreme value theorem says that if f is continuous on a closed interval a to b, then f has both a minimum and a maximum on the interval. And your keywords here are closed interval, so that means you're including your endpoints, and the word continuous. So if the function is continuous on a closed interval, you're guaranteed an absolute minimum or an absolute maximum. So you've got a continuous function on a closed interval. The highest point would be your max, and the lowest point would be your minimum. All right, now everybody always asks, what about a straight line? Yeah, let's say that that's y equals 5. If you have a horizontal line, then your maximum and your minimum are the same. So the absolute minimum, the smallest y value on that graph is 5, and the largest y value on that graph is 5. Okay, so that was absolute mins and maxes. Relative extrema, and we talked about this a little bit last year, relative extrema are hills and valleys. So a relative minimum is anywhere that you see a valley in the graph. So on this particular graph right here, and this is there should be arrows on the ends of that graph. What would my relative minimum be on this graph? 2, -4. And if a relative minimum is a valley, what could we call a relative maximum? A hill. Good. Or a mountain. Or a peak. Pencil top. Okay, where is the relative maximum? 0, 0. Okay, good. So make sure that you understand the difference between an absolute minimum and maximum and a relative minimum and maximum. The absolutes are the very highest and lowest point, but a relative is any hill or valley. These are also called local extrema. So if your book or something else that I give you asks you to find local extrema, we're talking about the relative extrema. Okay. Find the value of the derivative at the indicated relative extrema. All right, well, f of x is 9 times x squared minus 3 over x cubed, and we are looking for the derivative at the point 3 comma 2. So I want to find the derivative. I basically want to find f prime of 3. Do you want to use the quotient rule? Okay, if you were to look at it, what would it be? You think it's 0? Okay, well, let's just verify it. Let's talk about that. All right, instead of using the quotient rule, what I would prefer that you do is rewrite this as 9x squared minus 27 all over x cubed, which is 9x to the negative 1 minus 27x to the negative 3. So therefore, f prime is negative 9x to the negative 2 plus 81x to the negative 4. And f prime of 3 is going to be negative 9 over 3 squared, which is 9, plus 81 over 3 to the 4th, which is 81. So sure enough equals 0. All right, on part B, f of x equals the absolute value of x. What would f prime of 0 be? It doesn't exist, or it's undefined. Well, right, does not exist. Why does it not exist? It's a cusp, right. The derivative coming in from the left side is negative 1, and the derivative coming in from the right side is positive 1, and then so at that cusp, we don't have a specific derivative. All right, let's, on part C, we're talking about f of x equals sine x, and that point is x equals pi over 2. But what can you guess this derivative is? 0. So, at a relative extremum, which extremum is the singular of extrema, that sounds very weird. So, at a relative extremum, the derivative will always be either what or what? 0 or does not exist. All right, that brings up another vocabulary word, which is a critical number. If f is defined at C, and if f prime of C equals 0, or if f prime of C is undefined at C, then C is called a critical number. So a critical number is anywhere that the derivative is 0 or undefined. You've got to get that in your head and keep it there and not lose it. So relative extrema occur only at critical numbers. All right, so if f has a relative minimum or a relative maximum at x equals C, then C is a critical number. But the reverse is not true. If C is a critical number, you're most likely going to have a min or a max, but not for sure. Okay, so that's relative extrema. Absolute extrema could occur at a critical point? Or where else could an absolute extrema occur? At an end of the function or an endpoint. Very good. And that's what the rest of this section is about, is absolute extrema. So we're going to be looking for our absolute extrema at critical points or at an endpoint. Okay, locate the absolute extrema on the interval of f of x between -1 and 2. Whenever I ask you to find absolute extrema, I'm always going to give you an interval because, back to the extreme value theorem, if your function is continuous on a closed interval, you're guaranteed a minimum and a maximum. All right, so we're going to look for two places. We're going to look for critical numbers, and we're going to look at the endpoint. Let's start with the critical numbers. Critical numbers are where the derivative equals what? 0 or undefined. So the first thing I need to do is take the derivative. So the derivative is 12x to the third minus 12x squared. And I need to know where this derivative either equals 0 or where it's undefined. Is that derivative going to be undefined anywhere? No. It's a polynomial. A polynomial is never undefined. Yes, we do get to factor. So if I want to solve this equation for x, what could I factor out? 12x squared. And I'm left with x minus 1. So my critical numbers are x equal 0 and x equals 1. All right, now, my absolute extrema will occur at a critical number or at an endpoint, and the absolute maximum is the biggest y value, and the absolute minimum is the smallest y value. So I am going to go back to Algebra 1 and make myself a little t-chart of my critical numbers and my endpoints. So my critical numbers were 0 and 1, and my endpoints are -1 and 2. Now, that's just coincidence that I'm including all of the integers between -1 and 2. Okay, I have -1, 0, 1, and 2. That's just complete coincidence that it's all the integers between my two endpoints. So, all right, and then I just need to evaluate the function. So I'm going to plug 0 up into the original function, and I get 0. I'm going to plug 1 into the original function, and I get -1. I'm going to plug -1 in, and I'm going to get 7, I think. And I'm going to plug 2 in, and you get 16. Very good. That was fast. All right, so what is the biggest y value? 16. So my absolute maximum is 16, and my absolute minimum is -1. Good. Actually, I really would rather just focus on the y values. So let's just focus on the y values of the absolute min and the absolute max. Okay? That's all you have to do. Yes. Right. Kelly? Okay, the difference between, this is a good question, the difference between absolute and relative extrema. The absolute extrema, you have to have a closed interval to be guaranteed an absolute extrema. So anytime I'm asking for absolute extrema, it will be on a closed interval. And it's the very highest point or the very lowest point. And then the relative extrema are any high point or low point. So now that's not to say that one of them couldn't be both. Like if you have a function that looks like this, then you have two relative maximums and a relative minimum. Do we have an absolute maximum? Yes, we'd have an absolute maximum here. Do we have an absolute minimum? No. And that's okay because I'm not on a closed interval. My domain is -infinity to infinity, so I'm not guaranteed of an absolute min or a max. I could have one, but I'm not guaranteed it. Gray? All right, same thing. Find the absolute extrema on this interval between -1 and 3. So what's the first thing I need to do? Derivative. So the derivative is 2 minus 2x to the -1/3. And I need to find the critical numbers. So the critical numbers are where the derivative equals 0 or where the derivative is undefined. Is this derivative undefined anywhere? When x equals 0, because we could rewrite this as 2 minus 2 over x to the 1/3. So f prime of 0 is undefined. Right, because 0 is in the denominator. Now, do you think it's possible to find another value of x where this equation happens to equal 0? Sure. All right, so I am going to, if I set it equal to 0, I'm going to add 2 over x to the 1/3 to both sides. Equals 2. Can y'all look at that and tell me what x needs to be? 1, right. If you cross multiply, you get 2 equals 2x to the 1/3. Divide by 2. 1 equals x to the 1/3. What power do I raise both sides to? The third. Okay, so x equals 1. All right, so my little t-chart, I'm going to use where the derivative, my critical point, so where the derivative is undefined or 0, and the endpoints. Whoops, -1 and 3. And to save time, I will tell you that when x is 0, f of x is 0. When x is 1, f of x is -1. When x is -1, f of x is -5. And when x is 3, f of x is -0.24. Yeah. You wouldn't point that -0.24 is a rounded answer. So yes, if you had to use your calculator, I would let you use your calculator. All right. So what's the minimum value? -5, and the maximum value? 0. Good. All right. So the very bottom of this just kind of sums up what you need to do. First off, to find absolute extrema, you must have a continuous function on a closed interval. Find your critical numbers, which is where f prime of x equals 0 or is undefined. Evaluate f at each critical number. Evaluate f at each endpoint. And the least of these values is the minimum. The biggest is the maximum.